Hello and welcome back again. So for this video, the goal is to do another optimization. It's our fourth and last optimization video. And we want to build a rectangular storage container that has a volume of 10 cubic meters. It has an open top and the length of the base must be twice the width. So this information here will give us our constraints in a few minutes here. In the meantime, we have material for the base costing $12 per square meter and material for the sides costing $8 per square meter. And we want to, of course, hopefully build the minimum cost box. So again, we want to minimize the cost subject to the constraints in the problem. So first thing I'm going to do is try a little bit of artistic drawing, I guess you could say. And we're going to draw a rectangular box and label our sides. So you don't have to draw the whole box and be complete with it, but we definitely want to go through and draw this as best we can so we have a nice example to look at. All right, so now let's go through and label it. We're going to call this our length L. This dimension here will be our width, and then going up, of course, will be our height. So we know the volume for any rectangular solid is going to be length times width times height. And that must be locked in at 10 cubic meters. And we also know that the length, L, must always be twice the width. So these two constraints right here will help us reduce our cost function down to a single variable. So the next thing to do is now assemble the cost for this box. And that cost function, again, is going to have a total of 3 variables. And remember, it has an open top on it, so we don't have to use any materials for the top. Therefore, we get a price break on that. So we know that the dimensions for the area of the bottom is the product of those two measurements. So that's L times W. And again, it's going to cost $12 per square meter for those materials. So that's going to be 12 times L times W. Again, cost per unit area times amount of area. And then for the others, we actually do have 2 sides for each one, front and back and side, left and right. So we're going to have a 2, and then we're going to have an 8, because that's the cost per square meter. And then we'll look at the left and right first. That's W times H. Then we'll do the front and back. There's 2 of them. It's 8, and then it's going to be L by H. So our cost function is 12LW plus 16WH plus 16LH. And now we have to reduce this down to just one variable. The length is really easy because we already have an equation for it. We know that these L's are all going to be swapped out with 2 W's. But it'd be also nice to eliminate the H's as well. So if we go back to our original equation, we know that L times W times H is always 10. And if we divide both sides by L and W, we know that H is equal to 10 divided by the product LW. And then we know that we can replace the L with 2W. So we actually have 10 over 2 W squared for the height. So we can now take our cost function and just have it all in terms of the variable W. And again, that's going to be 12 times the L, which is 2W, times W, plus 16 times W, times 10 over 2W squared. And then we're going to have 16, 2W, and then 10 over 2W squared. And we'll draw like a little separator there just to kind of keep these things apart from each other, because things are getting a little big there. All right, so let's see if we can combine some like terms and clean this up. And we'll keep using black instead of green. All right, so the cost as a function of W will be 24W squared. My middle term will have a 160 as a coefficient. and that'll be divided by 2, so that's going to be 80 over W. And then my third term will be, looks like 160 over W as well, because we're going to cancel out one of the W's and the 2's cancel. And the last two terms are like terms, so we can combine those even further. And we will have 24 W squared plus 240 over W. So this is our cost function after all of that work. And for this cost function, what we want to do is we want to minimize this cost. So to minimize it, we're going to once again use the rules of calculus. We're going to take the derivative, find the critical numbers, study the derivative at and around the critical numbers to see when it's increasing and decreasing, and then from there we can answer our question. So our derivative, C prime of W, is going to be 48 W, and then it's going to have a minus because that's a W to the -1 power in our denominator. Or, well, when it flips up to the numerator, it becomes a -1. So that's going to be minus 240 times W to the -2 power. So my cost derivative is 48W minus 240 divided by W squared. This is undefined when W is equal to 0, but it's not a critical number because W cannot equal 0 because it's not in our domain. We could never have a volume of 10 with a width of 0. So we know that W cannot be equal to 0 in our calculations. So now we're going to set this derivative equal to 0. It's going to be 48W minus 240 over W squared equals 0. Because it's a rational equation, we multiply by the LCD, which is W squared on both sides. It's going to give us 48 times W cubed minus 240 is equal to 0. So W cubed is equal to 240 divided by 48. So W cubed is equal to 5, which means W is the cube root of 5. So that is going to be the width of our rectangular box. Once again, we draw a number line, put our derivative of our cost, put our critical number on it, and then look at the sign of our derivative on both sides of it. Well, something smaller than the cube root of 5 would be the number 1. And if you evaluate your derivative at 1, it is a negative number. So we have a negative derivative for values of W less than the cube root of 5. And then if we take something bigger than the cube root of 5, such as the number 2, and substitute that into our derivative, you will notice that it is going to be a positive number. And any value from greater than the cube root of 5 on is going to be giving you a positive derivative. So we've got a positive C prime on that side of our number line. So we've got cost decreasing to the left of the cube root of 5 and cost increasing to the right of the cube root of 5. That makes the cube root of 5 a true minimum. So again, we've got W equals the cube root of 5. And again, those were meters. We know that the length is twice the width. So L is going to be just 2 times the cube root of 5 meters. And then the height will just be 10 divided by that product. So that'll be 2 times the cube root of 25. So that's really 5 over the cube root of 25. And we can actually rationalize this as well. So if we do that, we would multiply by the cube root of 5 above and below. And that's going to give us 5 times the cube root of 5 divided by the cube root of 125, which is just the number 5 as well. So we're going to end up with the cube root of 5. And again, unit is meters for the height. All right, so we have the width and the height being the same, and the length is just twice that. And then for our cost, which is going to be kind of on the messy side, the cost from having the cube root of 5 is equal to, where did it go? 24 times the cube root of 5 squared plus 240 divided by the cube root of 5. And then we can actually get a decimal approximation for that. And that works out to be roughly $210.53. So that's the cost of building this rectangle, which again will have a volume of 10 cubic meters, and it's going to have dimensions that are cube root of 5 by cube root of 5 by 2 cube root 5 meters.